Sensors are everywhere. There's dozens of them in your car. There's potentially thousands of them in airplanes and trains. And our homes also continues to have an increasing number of sensors with a broad range of applications. They can be very useful for environmental monitoring, for medical and health reasons. They increase the security of our homes, a part of the entertainment portfolio, and of course we can monitor the transportation of goods as they progress, for example, along certain routes. And there's a huge range of military applications, defense type applications as well, let alone the various industrial control applications. So as our world becomes smarter and smarter, more and more sensors are expected to be deployed, but their full power really only comes to life when they are connected and when they are communicating with each other. So in this context, the range of design objectives in wireless sensor networks is extremely diverse, and of course this treatise can only look at a variety, a reduced fraction of the various design objectives seen in this slide. More explicitly, perhaps the cyan-colored little blobs indicate the quality of service requirements, the bit error ratio, the network lifetime, the resource limits, implementation and complexity, network topology aspects, network size, and interference management. These are all issues that are touched upon to a certain extent in the paper. And then there's the gold or yellow colored blobs, which are issues somewhat tangentially relevant in the paper, and those surrounded by the dotted lines, these are issues that are beyond the scope of this brief treatise. So moving on, the routing problem is of course a huge problem in connected sensor networks, and as the network size increases, the number of distinct non-looping routes increases dramatically, as seen in this little table. And so the full search-based brute force algorithm is typically unrealistic in practical applications, since, as I mentioned, a huge number of nodes has to be considered. So this paper looks at a limited subset of the potential design issues, and this simplified flowchart indicates the main thrust of the paper related to the benchmark scheme, which is the exhaustive search-based technique, and again this can only work for a limited size network, as well as the genetic algorithm-based solutions, which are single objective genetic algorithms, although interestingly, because we will be looking at the lifetime computation of these wireless sensor networks, these wrap up a number of related issues, including the integrity expressed in terms of the bit error ratio, as well as the power dissipation of the network. Other aspects such as delays, for example, are beyond the scope of this particular study. But what is clear is that we are able to create longer hops if we invoke a higher transmit power, and in this scenario, of course, the routing might have a lower delay. However, the integrity might suffer, and overall the network lifetime might suffer. So the route selection scheme and the battery level control are all feeding into the network lifetime computation. So these two algorithms are discussed in great detail in the paper itself. Perhaps I could stimulate your interest with the aid of this simple example, which is constituted by 6 nodes. And of course, the most crucial issue is how much charge the individual batteries have. Now, there is at least a dozen different definitions of network lifetime in the literature. We listed these in the paper, but what is quite crucial is, of course, that the source node does have sufficient battery power in order to transmit the message between the source and the destination via the diverse routes through the network. So each of the batteries are assumed to have a total energy of 5,000 joules, and as the routing progresses, we can see in the top right hand corner that this particular node here is now depleted in terms of its battery charge, and that limits the potential number of routes. Of course, the scenario is even more complex when the nodes are mobile and they change places. So the continuous lines indicate the valid and potentially available routes, whereas the dotted lines represent those routes that are no longer valid or available. And so here at the bottom right hand corner we can see that the moment the source node's battery has been depleted, then the network lifetime has been exhausted. And so really let me just conclude with a quantitative set of results. On the vertical axis we have the number of cost function evaluations, which indicates the associated network lifetime evaluation complexity. And on the horizontal axis we have the number of nodes, again in line with the table that we considered in terms of the number of potentially available routes. It's very clear that the complexity of the exhaustive search algorithm becomes literally exorbitant, and therefore is off scale for more than 8 nodes. What is worth observing is that as we increase the complexity of the genetic algorithm, for example up to 21 generations from 12 generations, then the number of cost function evaluations is of course increasing, but it's interesting to observe this huge complexity gap that we have, for example, for 7 or 8 nodes between the exhaustive algorithm and the genetic algorithm. There's a lot more interesting quantitative results in the paper, so I would like to invite you to peruse the paper, and my hope is that you would find it interesting and thought-provoking.